All right, so this first one is just like problem one on the current homework. I talked about that one a little bit the other day, but I'm going to use superposition to deal with circuits with different frequencies. And I don't think here in lecture that I'll get a chance to go through the example two, but I might start it at a minimum. Okay. All right. So here we have it. All right. So what I want to find is V3. I want to find the voltage across that resistor that is R2. I want to find that voltage right there. And I've got this circuit, and I have two sources. One is 5 volts. The other one is 10 sine 4000 t plus 40 degrees. Okay. Now, first of all, whenever I have two things at two different frequencies, I talked about this the other day, right? The process that we have to deal with anytime we do this analysis basically is the fact that the impedance depends on frequency, right? So I cannot solve for phasors at two different frequencies, add them together and convert that back. We talked about what our process is. The real world looks like this. So you could go in the lab and you could build this. You have a function generator giving you 5 volts over here. You have another function generator on the other side giving you 10 sine 4000 t plus 40 degrees. Totally can have that. All right. The thing about that is you would not be able to do your analysis with both of those sources turned on if you wanted to do it in steady state. If I wanted to get the differential equation, I could do that. All right, but I would have to solve the differential equation approach. All right. If I want to do steady state analysis, I got to get the phasor for V3 at DC, 5 volts, and at 4,000 radians per second. Okay. So in this case, I analyze the DC, I analyze the 4,000 radians per second, and then I convert them back into the time domain. So one question is at DC, right? What frequency are we talking about at DC? We're talking about omega equal to 0. So if you think about a capacitor, right? So a capacitor Z sub C equal 1 over j omega C. If I have omega equal to 0, what is that impedance? Yeah, it's infinite, which means what kind of component am I looking at? An open circuit, right? Now, we've said this before, right? In DC circuits, when you guys had first order, second order circuits, we had DC sources when we dealt with those, right? Like this circuit that I'm looking at here, what order is this circuit? This is a second order circuit, right? It's just I'm not worried about the transient response. When we did transient responses, we had DC sources always. All right. It's not to say that we don't have one here. We just don't worry about it typically. We're only worried in this AC circuit analysis piece of the class about what's the steady state response. Okay. If I had a second order circuit and I was worried about the transient response and I had only DC sources, you always say in steady state, what does the capacitor look like and what does an inductor look like? So when you had DC circuits, you said a capacitor in steady state is a what? An open. All right. You said an inductor in steady state is a short. That's entirely consistent with these two relationships. All right. ZL is j omega L. ZC is 1 over j omega C. If omega is 0, what's the impedance of the inductor? 0, right? It's a short, right? It's entirely consistent with what was said before, right? It should be, right? We don't just make stuff up. It has to be consistent with whatever the physics is, right? So, all right. That's just an important point for us to remember, and it makes the analysis hopefully kind of simple when we deal with the 5 volt source. But I basically have to use superposition. Now, one thing I want to remember here, so V1 was 10 sine 4000 t plus 40 degrees. I got to convert that to a cosine, right? So the way that I do this, if you don't remember it, basically is here is sine, here is cosine right here. The question I ask myself is, how would I have to shift cosine to turn it into sine? And I look at this and I'm just looking at the picture, right? How many degrees do I have to shift cosine to turn it into sine? 90, and it's a negative 90, right? Because I'm pulling it essentially backwards in time. I'm pulling its peak to a later time. Okay. So if I had 10 sine 4000 t minus 40 degrees, what's that as a cosine? Four thousand t, 400 t, 4000 t. So yeah, plus 40 minus 90, which will be minus 50 degrees, right? If you could also, I think, do plus 270 degrees. In other words, you could have pulled cosine back 270 degrees, would have been the same thing. It's actually an infinite number of choices that you could have if you really want to think hard about it, right? But let's not think too hard, right? It's a minus 90. So what's the phasor that goes with that? Angle 10 angle minus 50. Okay. Now, similarly, the other thing I have here is the 5-volt source. That's also a cosine, right? It's 5 cosine what? 0t plus phi. All right, it's plus phi, right? Now that phi doesn't really make any sense. I can't have a phase shift, so it's 10 cosine 0t, which is what? Phi. So it's also a sine wave, if you want to think of it that way. Okay. Yeah. Yep. So, and the way to think about that is, it's the omega is basically 2 pi over the period. The period we say is infinite because it's sometimes people want to say is the period 0. The period by definition is how long it takes for it to repeat. But basically, because it never changes, you'd have to wait forever for it to actually make some change. That's the way we think about it. The frequency is 0. If there's no variation at all, the frequency is 0. Right? Okay, so here's the circuit. First thing I'm going to do is turn off the DC source. So the way I'm going to say this is I'm going to say, well, V3 is going to be, how did I say it? V3 4000. Okay. So phasor wise, when I write lowercase, basically the phasor for that would be uppercase like that. All right. So V3 here should be equal to what I'm going to call V3 4000 plus V3, I think I called it DC. Is that what I called it? The V3 0, I guess I called it. V3 0. There's okay. All right. So the V3 4000 is with the DC source turned off, and the V3 0 is with the 4000 radian per second source turned off. Okay. So, all right, let's do that. So there's our circuit picture. All right, I'm going to turn the DC off first. If I turn the DC off first, how does that simplify the circuit here? If I turn a source off, a voltage source off, what's it become? A short. All right, so the 5-volt source there basically goes to 0. And my circuit becomes, yeah, so it becomes V1. And then there's an inductor L. I think I called this guy R1. And then, yeah, so then there's the capacitor and then there's R2. So basically it's the capacitor here, C, and then R2 is right here. And we turn the voltage source off. So that's our circuit. Now, I am looking for the voltage here, which I'll call V3 4000. Now, what should I do? What would you do? Yeah, I look at this and say I got 3 things in parallel here, right? And that's the way I would do this. You could do, if you did mesh analysis, it'd be nuts. All right, first of all, you could do that, right? But that's crazy because I got 3 meshes, but it'd be a lot of work. I could do nodal analysis, right? How many nodes do I have to solve for here? 1. All right. But for me, this is one where basically if I look at this, I've got a voltage divider going on. So one of the things I like to do here is R2 and C are in parallel with each other, as you guys have already identified. So I usually like to draw it like this now. Here's R2. And now it's a little easier for me to see that I've got the same voltage across all 3 of those guys in parallel. All right. So if I want to find V3 4000, for me, what I've got is a voltage divider, right? How do I have a voltage divider? What do I do with those impedances there? R1, C, and R2. Give me an equivalent circuit. And for me, an equivalent circuit means I draw a line right here. Everything to the right of that line can get replaced with a single resistor or single impedance. So what would that be? What's that? Yeah. Right. So let's call, I don't know, what did I give it a name? I did. ZEQ1. All right. So I have basically this guy would get simplified down to here's V1, here's L, and here is this ZEQ1, like that. And the voltage here across ZEQ1 is the same as it is in the circuit above, right? Because ZEQ1 here is R1 in parallel with Z sub C in parallel with R2, like that. All right. So V3 4000 is the exact same in the bottom circuit as it is in the top, because I'm basically looking at the terminals of that circuit, right? So the terminals here that I cut, the whole idea of an equivalent circuit is from the perspective of the terminals, right? The circuits are equivalent. In other words, there better be the same voltage across there for the same current, which there is, right? That's what equivalent circuit means. So that's what I have. Now I see that I have a voltage divider. So if that's a voltage divider, how would I get V3 4000? If you don't remember the voltage divider relationship, that's fine. Basically, I got 2 impedances in series with each other, right? If I've got 2 impedances in series, how would I approach this? KVL. Yeah, I could do KVL. Even simpler in KVL, I probably would just say, well, I know that those 2 in series are basically 1 impedance. So if I know the voltage across a series combination of stuff, what's the current? V1 over the total impedance. That's the current through the circuit. So how do I figure out the voltage across any one of the impedances? Yeah, the current times the impedance. So basically it's the current, which will be in this case 1 over ZEQ1 plus Z sub L. So I'm careful not to say L, right? Because it's the impedance of the L. It's not the L value, it's the impedance of the L. That's the current in the loop times ZEQ1, right? That's basically a statement of Ohm's law, and it's not 1 over that, it's V1 over that, sorry. So V1 divided by this impedance, that's the current. That current times that impedance is going to tell me what that voltage is. Okay, questions about that? All right. What I do then is here's the way I code this up. One thing you'll notice is I try to be consistent with the way I try to do all this stuff here. So I wrote this in as I just put R1, R2, L, and C. I defined omega, right? And then basically what I did was I put in V1. I wrote down Z sub C and Z sub L. I then solved for ZEQ1, and then I plugged that all in here. Now, you guys don't like to do what I just did here, I think in general. Maybe some of you guys are getting used to it. But when I look at this is all in terms of variables. And I can look at those variables and I can match them up 1-to-1 with my equation. All right. I can get my homework done a lot faster when I can match up those things 1-to-1 with equations. One of these, I made the comment in the Discord last night to somebody, people, and rightly so, because it's the way your brain has been trained. You try to simplify and simplify and simplify and simplify and simplify. The more times I do arithmetic, especially with complex numbers, I know that I'm going to F it up, right? I guarantee it, right? There's no need to do that. If you want to, it's a good practice. I totally agree with that. This is a circuits class, not a math class, right? What I would spend your time, if you're going to you spend 3 hours simplifying your math on your problems, you're not making good use of your time. Take your time to focus on learning the circuits part of it, right? So I'm gonna get something to the way that I would deal with something like the thing that was put in Discord last night. But what I mean here to say is really just try it. You know, it's really a tool. You don't have to do it. Like if you're not comfortable with it, I get it. But if you look at this, right, you can see how you can really kind of put that stuff together in sort of a simpler way. All right. Now, did I write down what the actual number is here? Hopefully I did. I think I did. This guy works out to be, if I do the math, V3 4000 works out to be 2 with an angle of negative 140 degrees. Okay. All right. Now, I also have to do the same thing with the DC source. How do I do that? Short the other one. And more general, because I'm trying to be pedantic, I'll turn it off, right? Which works into being, because I turn off the other sources. Turning off a voltage source means its voltage goes to 0. A device that has a voltage of 0 basically is a short circuit. All right. So I turn that guy off. Now I can also make some other simplifications here, right? Look at this circuit at DC. What did we say was the frequency? 0. What's that mean about the impedance of the inductor? The inductor is 0, right? So Z equals J omega L. And the the capacitor is an open. Again, that's entirely consistent with what we did with DC circuits, right? So it's like I'm asking you to find the steady state result in one of those differential equation problems. Because when I do impedance, I'm doing steady state, right? So what's that mean about the capacitor and the inductor? Do I even need to put them into my analysis? No. In fact, it's kind of weird. If you actually went into MATLAB and you said like Z sub C equals 1/0 times C, I'm not really sure how it's going to react to that. It's probably going to say inf, right? So it's probably not a wise thing. So I actually would make the simplification to say, I know there's no current going through the capacitor. Okay, so what I would do here is I would say, all right, with this circuit, I turn off the source over here. The inductor was here and it became a short. I have R1 right here. Then I have the rest of the circuit. So there was a capacitor here. Then there was a resistor again. This was R2. Then there was the 5-volt source. So there's the 5 volts. And now one thing is important. I can't change the polarities of things here. We define the polarity of V3 to be what it is right there, right? In that image. So the plus terminal of that V3 is at the top of the capacitor, and the negative terminal is at the negative terminal of that voltage source. All right, I can't change that. If I change that, I'm solving for something different than what I started with. All right, so this guy is V3 0, like that. All right, now I can simplify that circuit too a little bit. It's already pretty simple. But what's true about R1? Yeah, so I have 0 ohms in parallel with R1, right? So 0 in parallel with anything is what? 0, okay? And again, think about how much current can be going through that thing. Zero current can be going through R1 because I got 0 volts across it. Okay. So basically, how does the circuit simplify? Yep. So here's R2 here. This guy is V30. And then I have my 5 volts like this. So what is V30? Yep. Given the polarities in this problem, that would be 5 volts. If I had the polarity on the resistor to find the opposite way, it would have been negative 5 volts. Okay. All right. So I found that so at this point, you don't say, like in superposition, you learned in superposition, I take the two things and add them together. It is not this phasor plus the phasor I found at 4,000. What is true is it's the voltage that this phasor represents plus the voltage that the other phasor represents. So basically what we have at this point, I'll write it this way, V3 4000 was equal to 2 angle negative 140 degrees, and V3 0 was equal to 5, like that. All right. So what I did here was I put together the way this guy looks. So I had to convert these both into the time domain, and then I add them. So V3 of t, the way you'd write this, you say V3 of t would be equal to whatever the corresponding time domain voltage is for that guy, V3 0 of t, plus V3 4000 of t, like that. So in this case, what phasor goes with this guy here, the 0 frequency term? Well, 5 cosine of 0t, so basically just 5. Okay. What about this guy? Yep, 2 cosine 4000 t minus 140 degrees. All right. So this guy becomes 5 plus 2 cosine 4000 t minus 140. Now I shouldn't have the picture sitting here. If I look at this, then this picture is going to tell you what's the maximum value of 2 cosine 4000 anything? 2, right? What's the minimum value of 2 cosine whatever? Negative 2, right? So when I look at this, the maximum value should be 5 plus 2, or 7, and 5 minus 2, or 3, and it is. Okay. So this is basically it's been shifted up. Term that you'll learn in electronics. It's been biased up. It's raised up. Okay, you'll learn that term bias later. All right, but that's a pretty common sort of thing to have. Okay. Questions about how I did that? All right. Important thing to remember about this is, again, this is the steady state voltage. If I looked at this, there would be some transient as well, right? And the transient would be over within usually a much, much smaller time than a single period. All right, so the transient, there is some e to the negative t over tau sort of thing going on here. We're not looking at it. All right, there always is a transient response, always a transient response, but we're only doing steady state when we do these AC circuit things with impedance. Okay. All right. Questions about this? Okay. All right. So I'm going to go to my next example. All right. This guy here, I want to find a Thevenin equivalent, which means I want to find Z equivalent and I want to find the open circuit. All right. Now, before I can get too far with this guy, I got to figure out how I simplify this thing down. So, where do I start? 120 in series with a capacitor. 120 in series with the capacitor. They are in series here. Well, before I even start simplifying this guy down, I'm gonna first say to myself, I need to get this in the phasor domain. Right? It's not quite there in the phasor domain here. What do I have to change with Mr. 120 over there? Yeah, I got to make that cosine, right? So the first thing is, so how do I do that again? How do I turn that into a cosine? subtract 90. So this guy becomes 120 cosine what? 300t minus 120. Okay. So that means the phasor that goes with this would be what? 120 angle negative 120. Like that. Okay. All right. I've got a dependent source here. And it's a voltage dependent voltage source, right? So it depends on a voltage somewhere in the network. Okay. So my first step is I'm going to use the node method in this case. All right. One of the things I said is I got no choice but to use nodal or mesh when I have a dependent source like this. I can make some simplifications. Like he's right. I have the negative J40 and the 120 are in series with each other. That's totally fine for me to do. But I really can't make any more simplification because that 10Vx source there is not a resistor. I mean, I can't, it's not an impedance. I can't simplify it down. Okay. All right. So I want to find VOC. VOC is here. So I want to find the phasor for it. And I'm going to use the nodal method. And I'm going to make some definitions here. I'm going to call the 12 ohm is going to be R1. The 60 ohm is going to be R2. R3 is going to be the 120 ohm. And then the capacitor Z sub C is going to be the negative J40. Okay. And I'm going to use the node method. And for me, what I'm going to do, anytime I do any of these things, I start defining directions and everything for myself. So I'm going to write down here a set of directions. And I'm going to define currents. I'm going to call this guy I1. I'm going to call this guy I2. Call this guy I3. I'll call this guy I4. All right, so I just defined a bunch of currents there. So I4 is the current in that 120. I2 is the one in the 60 ohm. I1 is the current in the 12 ohm, and I3 is the current in the capacitor. Right? No reason why I chose the values I did there. I just did. I like to write everything down first in terms of the KCL. So what I'm going to do is I'm going to do KCL at the VX node. All right. And I guess really I'm going to call this, if it's nodal analysis, I choose one node as the ground node. So usually, it doesn't have to be, but usually it's the one at the bottom. All right. So in this case, I'm going to choose the one at the bottom here. I'm going to call this guy V1. Or I guess I'll call it VX because it's already called VX, right? All right. And then this guy here, there's another one. There's VOC over here, right? And I mean, it could be right there as well. I mean, there's different ways you could do it, but I want to do it at VOC. Okay. All right. How do I do this? At the VX node, I have 0 equals. I don't want to do 0 equals. I like to say it as going in equals going out. So in terms of the way that I wrote this, the definitions I have of I1, I2, and I3. The VX node, how do I write my KCL in terms of I1, I2, and I3? Yeah, I1 is the current going in. It equals I2 plus I3. Okay. How do I deal with I1? I call this guy V. V minus Vx over, I'm going to call it R1. But it's right, it's 12. What's I2? Vx over 60. Yeah, which I'm going to call R2. Then what's I3?
Vx minus VOC over
Vx minus VOC divided by Z sub C. And again, Z sub C has got a negative number in it, right? Negatives start messing with my head. right? So I'd prefer to keep them just out of my head. All right, because the negatives start changing signs on everything. So I've got that. So how many unknowns are there in that? Vx is an unknown, right? As is VOC, right? Those are both unknowns for me. All right, now what about at the other node? What about at the other nodes? KCL at VOC node. What's that?
One, I three. Nothing but one.
I3 and I4 are both entering, yeah. So I3 is coming in here. I4 is coming in from the left. So basically I have 0 equals I3 plus I4. All right. So how do we do that? How do I do the I3? You got it. Vx minus VOC divided by Z sub C. What about I4 there? Close, right? It's 10 Vx because of, yeah, 10 Vx minus VOC. Right idea, right? Divided by what I'm calling R3. Okay. All right. Now I've got two equations and two unknowns. So for me, what I want to do is I want to organize those two equations. All right. And this was the thing where I would say I wouldn't do much more simplification than what I have right here, because it allows me to look at my MATLAB, look at the equation I wrote down on paper, and match them. Right. So what I end up with here ultimately is, so I wrote all that stuff down, and I get now, so the first equation was V over V minus, what was it? V minus Vx over R1 equals Vx over R2 plus Vx minus VOC divided by Z sub C. That should have been it, yep. Now what I'm going to do is I'm going to rearrange that guy to have all of the V. So what are the two unknowns here? What are the two things I don't know? Vx and VOC. So what I'm going to do is I'm going to get all the Vx's together and I get all the VOCs together. So I'm going to say, now V is a number to me. V was basically this voltage source. It's a number that I know. All right, so it's a known value. So I'm going to say V over R1 equals 1 over R1 plus 1 over R2 plus 1 over Z sub C times Vx plus, sorry, minus 1 over Z sub C times VOC. Now, what did I do? I basically grouped all of the Vx terms together. I grouped all of the VOC terms together. And then I have a constant over here. All right. What I'm going to do is when I put this into matrix form, this guy here is going to be for me A11. This guy for me is going to be A12. All right. And I'm not going to simplify any further than that, because I could simplify 1 over R1 plus 1 over R2 plus 1 over ZC, and I guarantee I will screw it up, right? I don't trust myself to do math like that, especially on paper. I know I'll screw it up. That's where I let the computer step in for me, because I can write down in MATLAB that expression for myself. All right, we're going to see that in a minute. All right, that's one of my equations. What's my other equation? Well, it was this one down here. All right, so 0 equals V1 minus VOC over Z sub C plus 10 Vx. Sorry, not V1, Vx plus 10 Vx minus VOC divided by R3. Okay. All right. That's the equation. So again, this guy, I don't need to do a whole lot of rearranging. What I'm going to do is get all the VX terms together and all the VOC terms together. So if I do that, help me out with that. How do I group all the VX terms together? Yep, exactly. 1 over ZC plus 10 over R3. Exactly. That's how I would group it. I'd say it's that times VX. And then I would say minus something times VOC. You got it. Yeah. So this for me would be what I would call A21, and I would call A22. I'm going to put that in matrix form, right? So the way that I end up writing this guy is like I have right here. So I rewrote those two equations here, right? And notice if you look at A11, all right, here's how I wrote A11. I defined all those variables for myself. R1 is 12, R2 is 60, R3 is 120, Z sub C is negative J40. And I don't do any simplification beyond that, okay? It's good exercise for you to do that kind of simplification, but, you know, this is a circuits class. It's more important to me that you can look at, I can look at this equation over here, and I can look at the equation over here, and they match, right? That for my small brain, that is the easiest way to try to track everything. All right, because once I start combining all that stuff, the intuition of the math is completely gone. It's just all numbers to me. Those numbers could be right, those numbers could be wrong. Numbers have very little meaning to me, but when I can match the equations, they got a lot of meaning to me, right? And I can usually do it without doing a lot of work, right? I can write an equation at each node, got it all, and then I can jump over to the math, okay? And let the computer do the math for me. That's my recommendation to you, all right? So if I do this analysis, I end up with VOC, this is the code, this code will work for you. VOC ends up being 835.2245 with an angle of negative 140.17 degrees. Okay. All right, so notice one thing I always do is I get my VOC here. I said V of 2. Why did I say V of 2? Given the way I set the matrix up here. Yeah, so if I look at this, the V value where I say V equals inverse A times B, I'm looking at this problem right here, right? Where the matrix here is A, right? So this is V. I want the second entry of V because VOC is the second entry of that particular vector, okay? All right. Questions about that? All right. All right, so then the next thing is to find Z equivalent. All right, so Z equivalent, in this case, I can't look at that circuit and say, all right, what's the impedance looking into those terminals? It's not going to work, right? So what do I have to do? I got to find a short circuit current, okay? So what I do is I find a short circuit current and I say Z Thevenin is VOC divided by I short circuit. Okay, so I put a short circuit on there. Okay. All right. So should have redrawn myself the circuit over here. So I have now when I do this, do I turn the voltage sources off when I do the short circuit current? Do I turn off the sources inside? I leave them on, right? So I have V over here. All right, I got R1. Okay, I got R2. And importantly, this is Vx. That matters a lot because I got a dependent source. All right, I got Z sub C up here. I've got R3 right here. I've got the 10 Vx right here. Node all the way across the bottom, and I'm doing short circuit current. I got I short circuit right there. Good. No, let me do it on time. Got 6 minutes here. All right. Okay, so it it could be they're both fine, right? I'm gonna do nodal again because I only have one node to solve for. Right? What node do I have to solve for? Yeah, this guy right here, Vx. Right? That's the only one I have to solve for. What's true about this node right here? It's 0. Right? Now, actually, I could solve for this node too, right? I don't know what that is. I mean, I know that it's 10 Vx. I have one node to solve for, but I have 2 KCLs to write. Okay. So I'm inclined with 5 minutes to go to pick this one up in recitation. All right. So why don't I stop early and we'll do it in recitation. All right.